Alright, hi guys. In this tutorial I'm going to explain what a JTL is, and in the next tutorial I'm going to explain how to install JSIM, how to simulate a JTL, and how to plot um, the results using MATLAB, and that's for Windows. You can do that with Linux as well, but it's a different process. Alright, uh, stands for Josephson transmission line. It's very important element of the RSFQ, or Rapid Single Flux Quantum Logic family. It's used dramatically, so it is used to pass flux from one loop to the other, and it can be bidirectional, so it can go both ways. We also use it to sharpen our pulse if there is noise in it, and we can also use it to add delay in the system on purpose, of course. So a JTL has two Josephson junctions, in this one at least, and you see that this is pretty much a squid, two junctions and inductance in between them, and they're biased by DC current. The junctions, those are the characteristics of the junctions, depending our process and pretty much our application to begin with. If it's analog or digital, the characteristics can be extremely different. The capacity, the normal resistance, the critical current is very huge, and the scaling factor, which is pretty much the area, are the most important factors. Both junctions are shunted with a resistor. The reason we do that is to eliminate unnecessary oscillation. So this is an unshunted response of the junction, and this is a shunted one. It kills the extra oscillations that they're really unnecessary. So we can avoid interference and false results pretty much. Alright, so we do have four inductors here. They're all 2 picohenries, and a load where we can actually measure, plot the results we get. We also have a voltage source. That's not actually how it works, but we will use that to simulate the flux pulse. So suppose that the flux excitation pulse enters the system. The first junction is biased with the current 70% of the total current, so that's 250 and 250 microamps. The total is 500. 70% of that is 350 microamps is what we give here, and half goes here, and the total current from this and that exceeds the critical current of the first junction. The first junction goes out of superconductive state. The flux goes in the loop. It does a 2 pi phase shift, so you'll see a response like that, actually like that. It returns again to the superconducting state. That's becoming pretty much instantly, and the flux stays trapped in here, and you can think like it rotates here. So what happens next depends from the total inductance of the loop. So we add all the inductors, and if it's big enough, large enough, it will trap the flux and will stay in this loop. If not, again the same thing, the current from here will add up with the bias current, and the second junction will behave exactly as the first one, where it will pass the flux to the next loop. We can actually measure the results here. So what you're actually giving is, this is your input, and that's what you get pretty much straight away for this occasion, and those values, and that's a 2 pi phase shift for the first junction and 2 pi phase shift for the second junction as well. Well, that's all. Also keep in mind that we mark the nodes. Keep this sketch. We're gonna use it when we create our JSIM, when we write our JSIM code. Yeah. So any comments or questions, just let me know, and I'll see you at the next tutorial. Cheers.